Okay, so now we're going to get into the details about the model and the parameters that we'll estimate. We'll start with that 2-factor model and then we'll generalize on up because you can have 3-factor, 4-factor, 5-factor as far as you're willing to comprehend and go on the number of factors. So when we thought about G treatments and used overall mean plus treatment effects, we had an extra parameter, remember? And we solved that via a constant. So we'd set that our convention, while there are many conventions out there, our convention in this book and our convention that we're using software-wise is to set that first effect at 0, and then the sum of the effects must be 0. The standard factorial model has an overall mean, the main effects for each factor, and the interactions. We have a lot of extra parameters now that we have this factorial models, and so we're going to have more constraints than we have for the 1-factor model. And here's what it looks like. So take some time and digest this. I think sometimes, I don't know about you guys, but for me, writing things down helps me comprehend it. So don't just look at this. Really, take the time to write it down, think about it, and make sure you understand this. What this is saying is that each observation, the ith first effect, the jth second effect, and the kth replication can be modeled using a grand mean, a main effect for the first factor, A, a main effect for the second factor, B, an interaction effect, and random error. So notice that kth replication, which is the number of samples per group, per factorial treatment combination group, is K. Notice there's a major simplification here, and this is where I talked early in the course about how balanced designs aren't necessary, but boy, do they make life easier. This is one of those cases where life is so much easier if we have a balanced design. So notice K is 1 up to N. We don't have an IJ subscript on the N, meaning we're assuming a balanced design. So each treatment combination, each say temperature and lemon juice combination has the same numbers of apples in it, for example. Notice the effects for I, or the levels for I, are 1 up to little a, j, 1 up to little b, and so forth. Now here's our constraints. The sum of all the main effects for A, I think this should be an I right here rather than an A. It should be I, alpha I equal 1 up to A. The main effects for B, the interaction effects, be careful here, the interaction effects when we sum only across the I or A levels, and the interaction effects when we sum only across the B levels are all 0. So this is what we had before, that this would be 0. But now we also say, okay, the other main effect is also 0, which seems obvious. That should be the case. But we're going to go further and say the effects sum to 0 when we sum over only one of the indices, the indice for A, the indice for B. G now is A times B. N is NAB, or NG. I like getting rid of G at this point. I don't really like that Gary started out with G, to tell you the truth. I would have started out with A and then generalized to A and B and so forth if I had written the book, but I didn't. So I'll go along with his notation, but at this point I just say our number of treatment levels is A times B. Our number of observations is N, because we have a balanced design, A times B. The degrees of freedom for A is A minus 1. Degrees of freedom for B is B minus 1. Degrees of freedom for the interaction AB is A minus 1, B minus 1. So this part we'd already seen, this row. But what about that error? Before it was N minus G, or now we call it N minus AB. Well, that is just A times B times N minus 1. And that makes a lot of sense, right? The math is pretty easy. Just plug in NAB here and factor out AB. So notice A minus 1 plus B minus 1 plus A minus 1 times B minus 1 is equal to AB minus 1, which before is what we call G minus 1. So this is why any factorial design, whether it's 2-factor, 3-factor, 4-factor, can just be thought of as the one-way CRD, where we make the number of levels just the combination of factor treatment combinations. So Any particular treatment mean in the table is the interaction effect. So first level of A, first level of B gives us our interaction effect for AB11. First level of A, second level of B, AB or alpha beta 1, 2. That alpha beta doesn't mean it's multiplied. I'd never thought to point that out to students before, but just in case you were thinking it was just that effect times that effect, that is not what we mean. We mean the adjustment for both effects being present, and that may be a positive value, that may be a negative value, it may be 0, but it's not a simple multiplication. If it were a multiplication, I'd have alpha I, beta j, and make it clear, but I never mean that. I'm glad Gary pointed that out. I wouldn't have thought that. We can decompose the data, and I think this is really useful to take a look at. So each mean, or each observation, is a function of the overall global mean, that's the main effect mean, or the global mean. The effect for the first factor A, so that's the ith mean summed over all the other indices, the B indice, the AB indice, minus the grand mean. The effect for the second main effect here. The effect for the interaction. Now let's pay attention more to this because this is kind of new. So it'd be that interaction mean. So that's the computed interaction mean, which is different than the effect, right? We know that now. Minus the mean for A, minus the mean for B, plus the global mean. Why do we have to add in the global mean? Well, we subtracted it out 2 times when we added in this mean and that mean, and in effect need to add it back in. Okay? Then the residual, which is just that observation minus that interaction mean. So if we plug it in using the effect notation, we get the global mean estimator. I would have put mu hat there personally, minus the first treatment mean minus the global, minus, now this is the part to pay attention to, the interaction mean minus everything else. Okay, so notice this is like the additive model right here. And that's really clearly separating off that interaction away from everything else that contributes to that observation, that part of that observation. And for the residual, same idea. The observation minus everything else, including the interaction now. So this makes a lot of sense. So this makes the sum of squares decomposition real clear. If we look at the sum of the yij squared, we're going to get each of those effects in there, quantity squared, because we have the squared there and there. If we multiply this all out, we would get the grand mean squared, the main effect squared, the main effect for B squared, the interaction effect squared, and the residual, that's it, residual squared, but we're missing something. Okay, algebra, what's missing? All those interactions, the cross products, I guess I should say. All those cross products are falling out. Why? Well, because we have a balanced design. This is one of the first cues we're seeing where balanced designs make things easy. Because of the balanced design, all those cross product terms are just going to be 0. You can start writing those out and think about why each of them needs to be 0 in here. And then you'll see that you really can go from this straight to this. Hence why we love to say balanced designs make life easier, or else this would be a far longer expression. So how can we go from here to here? Well, the sum over all the indices of the grand mean squared is just n times that grand mean squared. The sum over the jk, n times b, because remember k goes with n, j goes with b, times that effect. Here we have NA, because it's the other effect. Then we just have N for the interaction. We're still summing across the other 2 indices, and then we keep that whole sum. So then we see the overall sum of squares. This is the total sum of squares on the left-hand side, is the sum of squares for the constant Sum of squares for A, B, AB, and error. We usually just ignore this and don't think about it because we even if this is 0, we don't care. So here's how we fill in our ANOVA table for a factorial design. We have our row for A, B, AB, and error. Notice all of these sums of squares match what we got to here. So maybe write that model out. Sum of squares total equals this, which is equal to this. Make sure each of these sums of squares make sense. And this, of course, would sum to the sum of squares total at the end if we summed up this, 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 and this, right? Then we have our mean squares and our f-tests. So notice instead of having one f-test, now we have 3, one for the main effect of A, one for the main effect of B, and one for the interaction. The way it's written out here is the opposite of the direction I look at them. I actually look at this first. So if you print these out, you might put a number 1 here, number 2 here, number 3 here, and really 2 or 3 doesn't matter because that's arbitrary. What's A, what's B? We still reject for a big F, but we still need to check our assumptions and all the other things we've been talking about. So all those assumptions for the C or D that we talked about in chapter 6, I think it was, still apply here. Just because we've made it a little bit more complicated here doesn't mean we still can be lax about heterogeneity of variance or normality of the residuals or anything like that. The various sum of squares terms can be thought of as an improvement for your model fit, where your model is inherently the effect of A, the effect of B, the effect of A times B, or AB, not A times B. The sum of squares for A is the improvement in adding A main effects. The sum of squares for B is the improvement of adding B main effects when you already have A. The sum of squares for AB is the improvement of going from the additive model where you have the main effects for A and B to the full model with G treatment means. So if we see this as being non-significant, it means, well, that additive model probably suffices, but we still leave it in there because it is a good way to understand the effect of having no interaction in this case. Factorials with more than 2 factors are just like factorials with 2 factors. We just have more factors. So we have more subscripts, we have more data, we have more terms in that model, we have more zero-sum constraints. And here's his snarky side coming out. Gary says, and we have more confusion with higher order interactions. It does get, I have a hard time going beyond 3, to tell you the truth, and making sense of it in practical settings. Okay, but the ideas are just like the 2-factor. It's really no different. For example, we could entertain a 4-factor model here. Just take a little look at this. Here's our grand mean, our main effects, our 2-way interaction effects, our 3-way interaction effects, our 4-way interaction effect, and our residual error. So we could think about how this 2-way effect is how B effects change across levels of C. A 3-way effect would be how the BC interaction changes across levels of D. So even with 3-way, you're talking how the interaction effect changes with levels of the remainder 3rd factor. Okay, so we're not saying how both B and C main effects change across the levels of D, but how their interaction changes. Then with 4-way, this is where I start losing my mind because we're talking a 3-way interaction changes, which is dependent on how the 2-way interaction changes across levels of a 4th factor, which then that's each of those 2-way interactions are across a 3rd level entertained in this interaction, and it becomes a very complicated thing to think about at that point. Not undoable, but I really draw lots of pictures, look at lots of pictures, the interaction plots, and spend some time thinking. All right, so that's a good place to stop. We'll end with the notes here for this week.